Okay, today's lesson is kind of like too many lessons combined. We're going to look at a subject of drug testing, which is going to turn out to be another application of conditional probabilities. We saw that in the last lesson, right? And then we're also going to look at something called complements, which is kind of when you put the word not in front of something, it's called a complement. So anyway, it's kind of like two mini lessons in one. There is a common theme, though, and the common theme is just being careful with the way things are phrased, being very careful with the way things are phrased, because it can throw you sometimes. So anyway, let's look at drug tests. These used to be in the news a lot. I don't know why they're not anymore, but they used to be in the news a lot. They were kind of unpopular. But let's say we have a particular company or whatever, and it's testing their employees for drug use. And let's say we have this particular drug test that says, okay, we give this test to 300 people, and 143 come up with a positive result. Wow, it's almost half. But of those, 24 were false positives. In other words, they tested positive, but they weren't really taking drugs. See, that's interesting. You don't want a test that's not accurate, right? Well, there were 24 false positives, and it says here we also had some false negatives, 3 false negatives. Okay, and then we're asked some questions like, what's the probability of this and that? But before we answer those questions, I like to take numbers, especially when we got a lot of numbers all written out in a sentence. Try to put them in like a table form, some kind of shortcut form. I need to try to spin this a little bit. Okay, let's see now. 300 people given a test. Okay, that means everybody adds to 300. Cool. Among 143 with a positive test result. Okay, let's talk about people with positive results. Now, some of those people are on drugs, and some of those people are not. So this is how we'll organize our table. So we'll have like 2 rows, 2 columns. So positive results. 143 were at positive results. Now it doesn't say there's 143 here. It doesn't say there's 143 here. It says there's 143 total. So those 2 numbers will add up to 143. Now, but the next thing they're saying is that 24 were false positives. Okay, that means you got a positive result, but you're not on drug. False positive, 24. Okay, see, now we're getting somewhere. So 24 false positives, 143 total. So 143, take away the 24 is, what the heck is that, 119 or something? Let me see. 29, 39, 43. Yep, 119 go there. Okay, we've got one of our things filled in here. Cool. Now, you could get a negative result, of course. So we'll have more numbers down here. Now, they did say right there 3 false negatives, which means you got a negative result, but you really were on the drugs. So the 3 goes there as the false negatives, right? So keep that in mind. These are the false positives. These are the false negatives, right? False positive, you got a positive result, but you're not on the drugs. False negative, I got a negative result, but hey, I'm taking the drugs. Something like that. Okay, so let's get this stuff erased. Okay, cool. Now, how do we figure out this number? Well, we know there were 300 total. So if 143 are over here, it must be the rest in this column, or excuse me, row. So what is that? That's 157 total in this row, right? Okay. So if that's 157 total, and that's 3 of them, then I guess this must be 154 right there. That's nifty. We got our table. That's every possibility, right? Every possibility is it comes in 4 categories. Either you get a positive result and you're on the drug, or you get a positive result and you're not on the drugs. You either get a negative result and you're on the drugs, or you get a negative result or you're not on the drugs. I mean, what else could there be? That's all the possibilities right there. All right, now we can answer some questions. First one, what is the probability of an accurate test result? Well, going back to the basic way we define probability, we define it based on counting things, right? So I'd want to count the number of accurate results, put that on the top, and then I'd want to count the total number of results, I guess. Don't have to count them. They told us it was 300. That'll go on the bottom. So the number of accurate results, where are the accurate results? I tested positive and I really am on drugs. That's a positive result, or excuse me, a correct result, an accurate result. And then what else is accurate? I got a negative result and I'm really not on drugs. It was, in other words, the test was correct. It said it was negative. I'm not on drugs. That's correct. So there's another 154 correct results there. And the total, you could add all four numbers, but of course we know that adds to 300 because that's how we figured out those four numbers in the first place. So there's 300 total, and if you work this out and turn it into a decimal, I got 0.910. 910? I think it was 910 actually. So 0.910, sometimes 3 decimal places is good for these things. So 0.910, about a 91% chance that this test is accurate. Okay, good to know. Next question, what's the probability that you test positive? Testing positive. Well, again, we'll go back to our basic, count things up definition of probability. You would count the number of positive results over the total number of results. And so the total number of positive results, well, actually, we'd need to add both of those together because you got a positive result here and it was right. You got a positive result here and it was wrong, but it was still a positive result. So the positive result is 119 plus those 24, and this is out of 300 again, 300 total results. Turn that into a decimal and I got 0.407, which is kind of saying about 41% of the people taking the test are going to test positive. Wow. What is the probability that someone on drugs tests positive? Okay, notice this phrasing. Got to be very careful with this. I'm going to be so careful, I'm going to use green. What is the probability that someone on drugs tests positive? Notice we have a given condition here. It's kind of asking what's the probability someone tests positive, but not just anyone. What's the probability that someone on drugs tests positive? So that's the given condition there. Whoops, I didn't want to erase that. This is what you call, and we saw these in the last lecture, a conditional probability. It's not just a probability that someone tests positive, it's a probability that someone tests positive when we look at the specific condition that they were on drugs. The condition is we're on drugs. The given. I like the word given. It's a little more natural to use. So if we accept that they're on drugs, then what's the probability they test positive? So we can write that kind of symbolically this way. We can say maybe I'll go back to blue. We can say the probability of a positive result. Come on, you stop moving. Probability of a positive result under the condition that, or given that, they're on drugs. Right? That's our notation with this vertical, we call that a pipe, this vertical thing here, this vertical line. Positive result, given that they're on drugs. So again, this is what's given, they're on drugs. Well, what is it? You would have to count the number of positive results for people on drugs, because it has to be you're just limiting yourself for people on drugs. And then you would divide that by the total people on drugs. Total number on drugs. The drugs is given. The drugs is assumed. When you're counting, you always assume this guy's on drugs, man. So the positive results for people on drugs would be right there. They're on drugs. It's a positive result. It's 119. So that goes there. Total number that are on drugs. Well, they're on drugs. They're on drugs, right? The 119 plus the 3, which of course is a 122. And if you take the 119 and you divide it by 122 and you make a decimal out of it, you get a 0.975. Holy cow, doesn't that look impressive? You want to sell this drug test, you use that number. You say, hey, look, if they're on drugs, it's a 97.5% we'll catch them. We'll catch someone on drugs. The test will show, hey, you're on drugs. We'll catch someone on drugs. 97.5% chance that someone's taking drugs, right? That's what we're given. If someone's taking drugs, it's going to test positive. It's going to get them. Going to get them. We're going to get them. Now, compare that. Let's get a different color for our comparison. Purple. Compare that to this number that we got up here. Right there, actually. Compare this. The test is 91% accurate. It's only 91% accurate. But look at this number, 97.5% that will catch them. See, it kind of makes you think, right? Because if I told you, the first thing I told you is it's 91% accurate, you're not going to be as impressed, right? So in other words, which number you throw at somebody, you know you're influencing their decision-making process. You have to be aware as the buyer, as the wise consumer, that, what's the number you're looking at? What does it really mean? What am I really interested? Is this really what I'm interested in? And that kind of stuff. 97.5% is a powerful number, but it's only 91% accurate. Okay, now, here's another question. This is my favorite question. Let's assume, without looking at this question yet, let's assume that you were tested, and you tested positive. And people say, hey, it's a 97.5% chance that it'll catch the druggie, and it caught you, didn't it? Ha, you druggie, you're a druggie. That's what you are. You're a druggie. So are you? You could say, oh, I protest my innocence. And they could say, well, it's only a 2% chance. We don't believe you because you got a funny look on your face or whatever. So anyway, let's look at this question. This question is very worth looking at. Let's put it that way. Let's go back to what? Blue? Yeah, blue. Boom. What is the probability that someone testing positive is on drugs? Now that's really the question, isn't it? In your case, you just tested positive. So given that you tested positive, what's the chance, the probability that you're actually on the drugs? That's a different question, isn't it? This says we're given that someone's on drugs. So what's the chance that the test is positive if they're on drugs? This is different. They tested positive. That's what we know. So what's the chance they're on drugs? That's what we'd like to know. Is it 97.5%? And the answer is no, it's not 97.5%. And as we see in a minute, this problem has a name, and it's called confusion of the inverse, and you got to watch out for it. It's not the same, and I'll show you that it's not the same. So if this is the given, back to my green, someone is testing positive is the given. Well then, what we're calculating is the probability that someone is on drugs, given that, under the condition that they had a positive result. See, the given goes here. But you can see, just looking at these two things are switched, right? Here the positive result comes first. The condition is on drugs. Here the on drugs comes first. The condition is positive result. See, that's why we get this word inverse, kind of like backwards kind of thing. Anyway, let's count it up. Let's figure it out. Let's go here. So what you would do is you would take the number of druggies, the number on drugs who have a positive result. Oh, I should write this in words to be consistent with what I did on the previous example. Number on drugs for those with positive results over the total number of positive results. And what is that? Well, we consult our table again. The number of people, I suppose I should erase these things. The number of people, what was I looking for? On drugs who have a positive result. Okay, so these are the guys with positive results, all of these people. Those are the ones on drugs, 119. And the total with positive results are 119 plus 24, which, well, it's going to be 143, but it's the 119 plus 24. So think back to when we did the previous problem. In the previous problem, it was we added up all the people that were on drugs. We added these two numbers, but this time we're adding these two numbers, all the people that are on positive results. So it affects your probability very directly. And if you work this out and you make it into a decimal, it comes out to 0.832. Now that's amazing to me. Get a load of that number right there. So you're walking around with a positive test result and everyone's going, oh my God, 97.5% chance. And it's like, no, it's only 83 for crying out loud. It's only 83%. So Again, confusion of the inverse. These numbers can be very, very different. Now, down here I have just a sort of a trivial example that I hope will drive home what exactly do we mean by confusion of the inverse. Compare these two statements. We know you did the crime. Why? Well, you were right there at the crime scene. Okay, that might come up in a court. Compare that to the sentence which is kind of written in the opposite direction. We know you were at the crime scene because you did the crime. Okay, now that, if you actually knew somebody did the crime, you could say, yep, they were at the crime scene. I mean, assuming it wasn't some kind of real weird cyber, I suppose these days it could be any kind of crime, right? But anyway, if you did the crime, let's say the crime was robbing a liquor store. We're going to assume that you were there to rob the liquor store, right? That would be 100% certain. But you were there at the liquor store does not mean you robbed it. So anyway, this comes up a lot in court cases where the prosecution is arguing and saying one thing and getting the jury to think one thing when mathematically that's not what they should be thinking. This might be the more convincing example now to think about it.
You know, that test will catch 97.5% of them, and they tested positive. I rest my case.
No, it's 83%. I protest my innocence. Whatever. Okay, you get the idea. So that was another good example of conditional probabilities. I liked that. Test results. Got to know about them, I guess. Now, mini lecture part 2. Something called the complements rule. Now, this is actually, this will be star of the show in our next lesson, but in this lesson I do want to just kind of introduce it. I guess I'll be purple for a while. The complements rule kind of goes like this. First, we need to get some definitions going here. So, you know how usually we call our events capital letters? So I'm going to say let capital A be some event, which means a set of outcomes, I guess usually we use the word favorable outcomes. Favorable doesn't necessarily mean good. It just means that we're looking for them. Set of favorable outcomes. We sometimes say, yeah, that's the event outcomes. Use them interchangeably. Anyway, the complement of A. The complement, spelled with an E, not an I. The complement of A. Often denoted, especially if you can get your typewriter to work right, often denoted a bar, encompasses all other outcomes. Everything else, in other words. All other outcomes, or you might say it this way, all those that are not A. All those outcomes that are not A. Okay? There's a rule that goes with it. It says, well, if you know the probability of event A and you know the probability of event A bar, or the complement of A, well, if this is everything that's not this, then guess what? That's every single possibility is being taken into account here. So those probabilities have to add to 1, because remember 1 means certainty. So it adds to 1 because it's certain that it's either A or not A. It has to be either A or not A. Right? So that's kind of one way of stating this, or another way of stating this is to say the probability of the A complement, the A bar, is 1 minus the probability of A. And that's the way the rule often gets used, is because it's like, hey, I know the probability of A. I'm trying to get the probability of A complement. Oh, I know, I'll just go 1 minus. Right? That's usually how the rule is used. Like in the next example. Change colors. Let's do green again. Biff rolls a fair 6-sided die. Fair, again, is just a shortcut way of saying all outcomes are equally likely. So a 6-sided die, it's got numbers 1, 2, 3, 4, 5, 6, 1 on each face. Find the probability of an odd number. Well, what you would do is you add up the number of odds over the total, right? Total number. And you would get, well, that's odd, that's odd, that's odd. So you get 3 odds out of 6 total outcomes, which is a half. Find the probability you get an even number. Well, of course, in this simple example, you could just do it directly and count the number of even outcomes divided by the total. And the evens are 2, 4, 6. So you get 3 evens out of 6, which is also 1/2. Now these are the complements of each other, which is why 1/2 plus 1/2 equals 1, which is why that's working. So I'm going to put here or with a new color back to purple. Or if you want to use complements, you could say, well, you reason this way. You'd say to get an even number is the complement of getting an odd number, right? In other words, if it's not odd, it has to be even. They're complements. Not odd means even. I guess I'll put it, not odd means even. The complement means put the word not in front, basically. If it's not odd, it's even. So I can say the probability of odd complement is 1 minus the probability of odd, which comes from there. And so it's 1 minus 1/2, which of course is 1/2. Of course you get the same result, right? But I just want to illustrate the use of this rule here. Okay, so if you know that you're looking for the complement of something, then the probability, you just go 1 minus the probability of the not complement, I guess. Okay, so that's it's not such a it's a straightforward idea, really. But you just have to be a little certain before you apply this rule. You just want to be certain. Maybe I'll put this in red, fuchsia. Just be sure before using this rule that you really do, or you really are looking at a complement. That's the part you have to be careful about. That's the only way you can really trip over this rule is if you think you have the complement, but you really don't. So this particular caution here, complement does not mean opposite. It's not exactly the same. It's not really the same thing. So I've seen this mistake made before. So the probability of drawing a red face card from a full shuffled deck is 3 out of 26. Okay, probability of a red face card is 3 out of 26. Make that 26 look a little better. Okay, so the question is, what's the probability of getting a black number card? Now you might say, well, red face, black number, they're completely opposite, right? So that must mean they're complements, right? So yeah, 1 minus 3, 26, question mark, question mark. And the answer is no. And the reason it means no is because, and I'll go back to green, because, and well, this diagram will drive home the point, I think. Where are the red face cards? There's the red face cards right in there. Green doesn't work very well on that chart, does it? We'll go back to fuchsia. Here are the red face cards right there. In fact, let's make that a little bit tighter. There are the red face cards right there. Where are the black number cards? Well, you got some up here, and you got some up here, right? So notice that the complement of red face card really is not a red face card. And not a red face card means it could be a red number. It could be a black face. In other words, it's a face card but not red. It's a red card but not a face. Or it could be a black number. It could be any of these. It could be any of these. It could be any of these. Not just these, right? So it's not really a complement. So this problem here, you would not be able to use that shortcut. You would just have to say, hey, look, they're just they're throwing me a red herring here when they give me the probability of a red face card. It's meaningless. They're just trying to throw me off. Trick question. Not supposed to do that. But so anyway, just to answer this question, what is the probability of a black face card? Well, we could do it directly. We could count. There's 10 there. There's 10 there. There's 20 black face cards. So we'll put over here, it's 10 plus 10 over the 52 in the deck. It's 20 over 52, reducing to 10 out of 26, reducing to 5 out of 13. And you can make that into a decimal and a percent if you want. But anyway, the caution here, again, just here's the point. Just be careful. Complement and opposite are not really the same. Put the word not in front. It doesn't mean it's... just don't use the word opposite. Okay, so let's practice defining complements a little better here. Biff flips 2 coins. Okay, go Biff. We're going to say the event A is he gets 2 heads. Okay, cool. Well, what would A complement be? The most direct way to say it is to say he does not get 2 heads. But it'd be nice to simplify that or boil that down a little bit more. He does not get 2 heads. Well, what does he get then? I want to know what he does get. Don't tell me what he doesn't get. What's he get? Well, if he doesn't get 2 heads, maybe he gets 2 tails. I'll put maybe. Maybe 2 tails. Maybe 1 of each. Maybe 1 heads and 1 tails. Right? In fact, you could, if you wanted to, you could, here's you. You could split this off. He either got, let's say, heads there or tails here, and then he either got heads there or tails here, right? So there's 4 possible universes. Gets 2 heads is here, and then all of these possibilities represent the complement. Either we got heads then tails then heads, or tails then tails, right? That would be the complement over here. It's not heads, it's everything else. Okay, cool. So I think what I'll say is at least 1 tails. That would be a really concise way to say this. At least 1 tails. He didn't get 2 heads. He got at least 1 tails. He might have got 1 tails. He might have got 1 tails and gone this way. He might have got 2 tails. Cooler filled with Cokes and Pepsis. You should try this one yourself. There are 3 drawn at random. Event A is getting all 3 Cokes. What does A bar represent? Well, basically, it would represent, if you want to be direct about it, you would say he does not draw 3 Cokes. That's not really the answer I'm looking for on the homework. Don't just put the word not in front and say, oh, that was easy. No, just work on it a little bit more. Think it through a little bit more. He did not get 3 Cokes. Maybe what he did get was 3 Pepsis. Now, again, you might think of that as the opposite. 3 Pepsis is the opposite of 3 Cokes. Doesn't mean it's the complement. The complement of 3 Cokes means not 3 Cokes. It could be 3 Pepsis. It could be 2 Pepsis and 1 Coke. It could be 1 Pepsi and 2 Cokes. But what these all have in common is that there's some kind of Pepsi in there somewhere, at least 1 Pepsi. And so that would be really the best way to say this. At least 1 is a Pepsi. No Coke, Pepsi. Okay, I think that's the end. Yeah. I said it was 2 mini lectures. What'd that take? 27 minutes. Hey, a new record. Woohoo!